All right. Well, good evening. We want to also welcome our friends on the live stream. My name is Drew Desker, and I'm the director here at Kopernik, and very glad to have you join us this evening. And again, especially those watching on the live stream. We had hoped we'd have a slightly better skies this evening because in about 3 or 4 minutes, the Inspiration 4 capsule is actually going to be flying over Kopernik. And then about 5 minutes later, the ISS is going to be right behind it. Unfortunately, the clouds are not really going to be working in our favor tonight. So, though we have in the past actually stopped the presentation literally right in the middle of it, we all go outside, watch it fly by, and then come back. But that's not going to happen tonight. But an inspiration for the those 4 normal people. What's the right term? General citizens that are currently in space. They return tomorrow. So there is another pass later this evening around, I think, 9:45. And if the clouds are going to give us an opportunity to do it, we'll certainly point that out and make you aware of that. Let's see here. Just I'm seeing a lot of new faces. Who's here for the first time? A fair number of people. All right, good. Who here are members? Oh, pretty much the rest of you. All right, excellent. Well, one of the things about a membership that I like to point out is that Kopernik is actually we're an informal education institution. We are a nonprofit. We're not really associated with any university per se. So it's events like this, our summer camps that help, and memberships help keep us afloat. We belong to what's called the ASTC, Association of Science and Technology Centers. It's a consortium of over 350 science centers, and your membership to Kopernik gets you into every one of those for free. So you could get into the Robertson Museum down in Binghamton, the Franklin Institute down in Philly, the Intrepid down in New York City, all for free. So if this is the kind of place that sort of resonates with you, you may want to consider getting a membership. Every Friday night from March to mid-December, we always offer a Friday night program regardless of the skies. And it's really giving us an opportunity to learn a little bit about how the world works, how the universe works. It's not always about astronomy. I mean, we're clearly a pretty decent public observatory. But like with tonight's program, we're actually looking down into the Earth and not looking out from it. And we're fortunate to have Dr. Nikulin from the geology department at Binghamton University talking about his research on seismic activity as it relates to fracking, and maybe he'll even talk a little bit about how Kopernik is going to help on that. So we're going to get your mic turned on there and give it a second. In a second. Wait a second.
Nope, guess not.
Try now.
Is that better? Oh, way better. Oh, wow. I hear myself. So weird.
Okay, we'll just give you a second here. We're going to turn the camera so that the people on the live stream can see it's a real person. And but we are going to switch over to his presentation, and we'll let you take him here. Thank you.
Thank you so much, Drew. Thanks so much for the invite, and thank you guys for coming out. I know it's Friday night, 8 p.m. So, but I am truly very excited to be here. When I first met Drew, I told him that the reason I look into the ground and not above, because the skies are so complex. I was terrified of it, and I thought it'd be a lot easier to look just inside our planet, because our planet is finite, right? We know how round it is. Well, it's not really round. We understand sort of the mineral composition of it. We understand how it works to an extent, but there are still mysteries and events that arise, and recently they started kind of essentially relating to our own activity, which is really an interesting phenomenon, right? Because we realize that we as humans, as these tiny little specks on the surface of the planet, can actually influence the way the planet behaves in more ways than one, as I'm sure everybody's aware. Okay, so specifically we're going to talk about the effects of fracking on seismic activity, and talk about if we have them, what they are, if when they do happen, and do we have them here specifically in the New York, Pennsylvania border. Because believe it or not, we're the world's most exciting laboratory for this kind of research. So we'll talk about that. Okay, so but first, I can't switch my slides. I don't know. Let me try. What happens if I do? I can't. Where's Drew? He ran away. Okay. Thank you. Sorry. Sorry, Drew. I think the. I know what it is. That's right. And there we go. All right, so the first thing I'm going to talk about is kind of differentiation between natural earthquakes and induced earthquakes, and the different types of induced earthquakes, and this brand new type of induced earthquakes that we started dealing with actually only about, if we're fully honest, about 15 years ago. Okay, so inside the planet, just like in your kitchen, the materials behave essentially in 3 different ways. Okay, any material can be either plastic. This is Play-Doh. This is something your bubble gum. This is a material that will take on any stress and change to that stress. You can't break it, you can't bend it, it just morphs into whatever shape you push it in. Okay? Then the opposite of that is brittle, right? You can't bend glass, it just breaks. You apply stress and immediately you get a response by the material shattering. And then there's this third type that actually everybody here is intimately familiar with, this elastic. This is a rubber band. Okay? And everybody knows what happens when you push a rubber band too hard. The material will deform up to a point, absorbing the energy, okay, similar to a spring. Okay, and once it hits its elastic limit, at that moment, okay, what happens when you pull an elastic band too hard? All the kids here. Yeah, is it a pleasant sensation? It's not. Why? Do you guys ever think of that? Like, what happens at that moment? Right? All that energy is instantaneously released into your little fingers, right? And it's not a pleasant sensation because you get impacted by the energy that was absorbed by that rubber band. Okay? And it turns out that rocks, we're so used to them on the surface, right? You go outside in the parking lot, you take a hammer to a rock, what's going to happen? Break. So what kind of behavior is that? Brittle, right? But if you slowly heat the rock up just a little bit by burying it, just by going below the surface, rocks begin first behaving elastically until they behave plastically. Okay? So there's this magical kind of zone from about 2 kilometers to about 20 kilometers in the crust where rocks will bend. They behave as elastic substances. They're able to absorb energy, and that means they're able to release energy when they are broken. So this is called an earthquake, right? Okay, here it is. This is your guide to every single news episode on earthquakes on CNN, Fox News, doesn't matter. Okay, the actual release of an earthquake, the actual energy release, is called a focus. Where that energy that propagates in kind of these wavefronts hits the surface, that's called the epicenter. Okay? Welcome to a life of annoyance, because now you will know when they confuse the two. Okay? If somebody says the epicenter of the earthquake was 15 kilometers below, you're like, no, nope, that would be the focus. The epicenter is always at the surface. The focus is the actual release point. Okay? Because you can't have a release of energy at the surface because brittle versus elastic. Very cool. Okay, so naturally occurring earthquakes occur in areas where we have movement of plates, where rocks are subject to some sort of stress, where they are strained by plate motion, okay, and that's where natural earthquakes occur. California, Chile, Alaska, any place where their plates are interacting, either converging, diverging, or sliding side by side, the famous San Andreas Fault, that's where you're going to have most of the Earth's natural seismicity. Here's a map. Okay? It's not random. Right? You see that most of the world's earthquakes are situated right where the plate boundaries are. Yeah?
What's the rumor that there's plates under New York?
Well, we're going to talk, yeah. So here's the thing. Right? New York, this is probably the weirdest map you've ever seen, right? Because it's not central on Europe or the US. It's central on the Pacific Ocean, right? Because that's where all the earthquakes are. New York is right here. That's actually the next slide. Okay? Do we have earthquakes? We do, right? Right? And that generally, those are related to either remnant stress from plate motions from millions and millions of years ago, or new plates can form too. Okay, we're not there yet, hopefully. Okay, but then comes this notion of induced seismicity. Induced seismicity has nothing to do with plate tectonics and plate motion. This is earthquakes from other sources. Okay, and there turns out there's a few ways you can generate an actual real earthquake without invoking the superpower of plate tectonics. Okay, when you fill a reservoir, for example, you can offset a fault. Okay, or when a reservoir gets drained, same thing, opposite effect. Mining, geothermal, explosions. Okay, how do we monitor North Korea's nuclear program? We can't go there. You guys ever wonder about that? We monitor seismic activity at the North Korean territory. We have seismic stations all around that country. Yep. Hydrocarbon development, right? When all those earthquakes were hitting California early in the 20th century, people thought there was some sort of new faults forming. It turns out they were just taking out the oil from all the old faults. Okay. I don't know if you've ever seen that movie, There Will Be Blood. Okay. That movie does not take place in Texas. It takes place in California. Okay. And kind of our focus for today is this notion of wastewater injection. Okay. It turns out when you take out oil or gas out of the ground, it does not come out like it does in the movie. It's not this black stuff that comes out of the ground. It's a mixture. It's a mixture of oil, water, and gas. Always. Depending on the fraction of each, that's the type of reservoir it is. And that water that comes out, it's not really water you can drink. It's all brine. It's not fresh water. It's mixed in again with all sorts of chemicals. So you have to dispose of it. And the most efficient way we've kind of developed to do that is actually we don't want to put it into the rivers. Is we just drill a deeper well, smart, right? And inject that water at even higher pressures below the surface. Okay. So sometimes double the depth of the actual well. Okay. And we've done this for decades. Okay. We've done this since the advent of kind of oil exploration in the 1900s. We've done this forever, and it was never really a problem. And you will see the reason in a bit. Okay, so again, 1945, we experimented with this, Wrangley, Colorado, famous injection experiments. Let's see how much water we can put down into a well and see what the effect is. It was the Army experiment. Okay, one of those 1940s, 1950s experiments, like let's see what happens. Okay, so we knew that there's a correlation between the amount of water injected into an injection well and possible earthquakes at a magnitude 4.9. Okay, and this is kind of the second learning moment that I want everybody to take away from this. Okay, earthquake magnitude is not linear; it is exponential. A 6.0 earthquake is 10 times stronger than a 5.0. A 7.0 earthquake is 10 times stronger than a 6.0. All right? Pop quiz. How much is a 7.0 stronger than a 5? 100. Who said that? Awesome. Thank you so much. Okay. People usually say 20. Okay. No, you have to multiply. Okay. So an 8.0 is not 300 times stronger than a 5.0 is 1,000 times stronger. Right? So we knew we could trigger 5s and 6s and even 7s in Uzbekistan here. Okay, and so all along, here we are into the 2000s again. We always knew this was a thing. Okay, but it was always manageable because we always had a certain amount of water that was co-produced with oil. So it was a linear relationship. Okay, and we essentially disposed dangerous chemicals from Army bases. We disposed geothermal. Okay, we disposed carbon dioxide for sequestrations, and we disposed, a little bit of tight shale and tight gas formation waters. Okay, and this is again one of those graphs that everybody should know. Here comes 2005. This is where we get our energy sources from. Okay. What happens right around 2010? is shale gas takes off. Leading to that are two technologies: horizontal drilling and everybody's favorite, fracking. Hydraulic fracturing, the idea that we can break rock to take the gas out of it. We can introduce porosity to a rock that is otherwise too tight to take out hydrocarbons off of. Okay? We drill a well, we turn it horizontally, we increase the pore pressure to a point where it starts breaking the rock around it. And once it does that, there's increased porosity. We prop it open with proppant, and oil or gas comes streaming back out and up the well. That is this is what allowed the U.S. energy boom, the U.S. energy revolution, right around 2005. And this takes off like wildfire. Okay, it's easy, it's predictable. The joke among geologists, you went from kind of essentially fishing to shooting fish in a barrel. Okay, it's two different problems. There was no longer a mystery as to whether there's oil or gas down there. We know right now where we're sitting. We know exactly where the Marcellus is, right below us. We need to drill to it. We need to turn the well. We need to frack. And you guaranteed production. This has never happened before. Oil was always a risky business. We de-risked that. And all of a sudden, we take off with the shale. Okay? So, when we do that, this is exponential growth. So we're producing more and more shale gas, which leads to a production of more and more frack water, which we need to dispose of. We don't have a certain amount of wells. How do you dispose more water into a well? You increase the pressure, right? And when you do that, you're triggering induced seismicity, okay? In areas where it is possible, okay? All right, so here's what I just talked about. Here's the turned well. Here is the frack, okay? Gas begins escaping into the well bore, moves up the well bore, and then is either put into a gas storage tank, and this water that is the frack water needs to get disposed of. Okay. All right. Here it is again. Okay. Frack water, and here it is the wastewater disposal well. Okay. Again, much deeper, much higher pressures because we're dealing with higher volumes. Okay. You know that what you need to do when you're trying to water, your plants. If you're trying to reach farther, if you're trying to put more water out there, you have to increase the water pressure. So it's a very simple relationship. Okay. And here's the problem. This is kind of what we sort of knew, but nobody paid attention to it. We talked about remnant stress. We talked about this idea that once plate tectonics, once those plate boundaries move, there's still remnant stress remaining. And what happens is, when you inject water into those faults that are already stressed, you're releasing it. You're triggering potentially more and more earthquakes. Okay? The injection itself relieves the effect of stress. Triggered earthquakes are more likely. Okay? But here's the thing. And this is where it's really important to understand this 1-2 punch of hydraulic fracturing. Okay? When somebody asks me, does hydraulic fracturing cause earthquakes? What is my answer? No. What's my more complex answer? Yes. Right? It triggers induced seismicity, but not directly. It's the excess water that it produces that needs to get injected that actually does the triggering. Right? But it's a chicken and egg thing. Right? So the simple answer is yes, the complex answer is no, or the other way around. Okay? But you need to understand that there's a one step in between there, okay, that does this. Okay? So large volumes that are disposed of through injection wells that come out of the hydraulic fracturing wells are the things that are the culprit behind this increase of induced seismicity. Okay? Okay? So here's some of it's kind of just a maximum magnitude graph. So we've pushed all the way up to kind of like the 6s and the 7s on the Richter scale. So these are pretty big. Okay. The rule of thumb. Excuse me.
What's the horizontal scale?
The horizontal scale is the maximum dimension of the fault. Okay. But here's what changed. So in 1970s in Oklahoma, so we had. Sorry, this is I think this is mid. Yeah, this is the mid-continent. So this is the square states. Okay. you had an average of about 21 events a year. In 1980, thank you, 31 events a year. 2005, 151. Okay? I'll show you some awesome graphs here. Okay? Arkansas, first huge reactivation of a remnant fault. Okay? Lots and lots, hundreds of earthquakes along a fault that folks didn't know was there before. Okay? Move over to Oklahoma. All right. This is an interesting graph. Let's see how you guys are on current events. So we said that hydraulic fracturing really takes off right around the mid 2000s. We have a exponential increase of seismicity right up until about January 15th, and all of a sudden goes down. Any ideas what happens right around here? What happens to the oil price? Oh yeah, this literally tracks the oil price, because again, remember the whole fish in a barrel analogy? If we know where to drill, we can stop at any time. Oil price goes too low, we stop fracking. We stop fracking, there's less water. There's less water, there's less pressure. And all of a sudden, we have a decrease in induced seismicity in Oklahoma. Okay? It conveniently stops right around here in 2017. Okay? What's the oil price doing lately? Oh yeah. Okay? Here it is. Here's the Baker Hughes rig count. So you can see that this is just the amount of rigs that are active in the area. This is printed on the front page of the Houston Chronicle every day. This is their weather. Okay. Rig count goes up and then drops right around 2015 as the price drops. And you can see that it's going back up again. Okay? So what about our backyard? Okay, that's the big question. That's why everybody's here. Like, so what's happening in Oklahoma? Oh, sorry, what happened in Pennsylvania and New York? Okay? Well, let's take a look. We know that theoretically all the faults are also stressed. We know that we have obviously been producing lots and lots of hydrocarbons here in Pennsylvania. Okay, this is Pennsylvania taking off again right around the time when we figured out hydraulic fracturing and horizontal drilling, 2005, 2006. Okay, Gasland. This is all the Pennsylvania kind of the oil rush, the gas rush of Pennsylvania around here. Okay, right around 2009, it really takes off. Okay, so we tripled production, quadrupled production in Pennsylvania over the last 20 years. Pennsylvania for a while was the #1 gas producing state in the union. Okay, step aside Oklahoma, step aside Texas. Pennsylvania was the #1 producing shale gas state in the union. Okay. Okay. This stops in July 2011. I put this other graph in here. You can see that it just keeps going. Okay. And here's our earthquake count. It does the same thing, right? Rises right here, falls. Well, no. Okay, always pay attention to scales. Okay, what is the number of earthquakes that we're recording in Pennsylvania? It's very small, right? So we're talking about 15 earthquakes. So we're not seeing a one-to-one correlation the way we did in Oklahoma, the way we saw in Texas, the way we saw in Arkansas. Okay, that's the good news. The big question, however, is, are we not seeing it or are we not noticing it? Because those are two different things. And this is the question of alligators in your bathtub. Having a small one is still not a great idea, right? And the fact you might have missed it and it's there. And this is where we set out to try to figure out if there are, in fact, induced events in Pennsylvania. Okay? So are we in for a surprise down the road? Okay. So we're gonna kind of take just a little bit of a pause here, okay, and kind of review what we've done so far. Okay. Injection or extraction of fluids at depth carries a risk of induced seismicity. Okay. Hydrofracking in and of itself, we just did that and then we dumped all the water in the river. Let's not do that. Does not carry an increased risk, for the most part, of induced seismicity. However, the rate is pushed up by the injection of the said water into deeper areas where, if pre-existing faults are present, it will trigger an event. Okay? And we're still in the process right now in 2021 of trying to understand the impact of hydrocarbon exploration and development in the Northeast, specifically right here in Pennsylvania, right here in New York. Okay. So here we are. We have an interesting situation. Right here, we're sitting on one of the most interesting natural laboratories in the world, because we have a red line that separates New York State from Pennsylvania. We have a line in the sand that separates equal geology and very different regulatory frameworks, right? We just drew a line, and it's a straight line, right? And what we're trying to understand, and I'll show you some. I'll share some of our initial findings in a second, is whether we're seeing any of these precursors that folks in Oklahoma would have missed because nobody was paying attention. And if we are, should we be concerned with essentially trying to regulate or trying to at least have some precautionary measures put in on both sides of that red line? Okay. So our phase 1 of our project was actually kind of an interesting one. We were literally trying to figure out if you can actively monitor a frac site. So all that information is nominally public. You can go on the Pennsylvania DEP website, see where the wells are going in, see when it is happening. But it gets a lot more complicated than that, as my poor student Chelsea figured out. It is very difficult to sort through that data set and actually figure out where you want to put stations out, which she did heroically. And we were trying to figure out in the initial phase of this is we call this the ambulance chasing project. If there's a frac that's going in, can put 3 stations around it and see if that frac is actually causing seismicity below it that would have otherwise been missed by the USGS network because it's frankly too sparse. They can't see the little stuff. Because again, alligators grow in your bathtub. They don't show up very big. Okay. So here is our results of our first deployment. I'll show you some of our stations. We deployed in I think this is Bradford County, Wyoming County, and another one in Wyoming County. 9 days, 2 days, and 24 days. The last one was kind of the big one. That's when we really figured out how to chase those wells. Here are the seismometers. They're about, the smaller ones are about the size of this cup. The larger ones are about the size of, I don't know, yay big. Okay, we have we put out a station that has a seismometer is essentially a very sensitive microphone. It is able to pick up those low frequency, kind of the thumping of an earthquake, of a small induced event. Okay. Here's our students digging these in. Okay, we try to be pretty discreet. Okay, here's kind of the final product. It just kind of looks like I don't even know what this looks like. It's like somebody left something for hikers or something, or some. So we have a battery in there. The sensor itself is dug in separately, and just this kind of. We try not to draw too much attention to these.
People know that you're doing it?
Oh, of course. We always. That's my big pitch in the end of this. So we can't do this without input from the community.
It's like, aren't a lot of these wells on private property?
They are.
People own it?
Yep. The good thing is we don't need to be on the property where the well is drilled. We can be about 3 miles out and still here. And here's the thing, and this is where it gets really this is actually a very important point. Induced seismicity, unlike climate change, for example, is actually it's a technical issue for both the companies and the general public. It's something that it's not something that either party wants, and actually the risk is manageable. It's leveling the playing field. It's getting away from this idea that they have the data and you don't. It's this idea that there needs to be an open public discussion. And if you're triggering induced seismicity, you need to lower your pressures. Okay, so it's actually that simple. But yes, we always ask for owners' permission to put these on their land, of course. Sometimes they do not want to be acknowledged in the papers because they have neighbors. Here are the 3 deployments, 3 wells, 3 stations around each. Okay, and here's a controlled result. We have an event. This is actually a very distant earthquake coming in. This is kind of just to verify that our station works. There's an earthquake, I think, in Greenland that comes in. This is how we check that, okay, the station is actually operating. And then we start looking through the data, and we look for stuff that's not in the USGS catalog, that is local, and that does not look like a mine blast or a truck going by or a helicopter flying over, because those are all events that are recorded by a seismic station. Okay, mining. The cool thing about mining and quarry blasts is they're usually during the daytime. That's when people actually work, right? They have very distinct waveform patterns that we're able to distinguish. They have a signature. Trucks have a signature for the most part. Helicopters do too. We're fortunate in that we don't have too much interference from helicopters and planes here. But here's what the data looks like coming off the logger. Okay, this is an example of a very clean earthquake, very well defined. PS, P wave, S wave, surface waves. Okay, and then here are some of the events that we code in. These are our suspects. So these are the events that occurred after a well was drilled, after the fracking has occurred. It cannot be linked to either a natural event or an event that we believe is induced by kind of a blast or some sort of a anthropogenic human activity. Okay, here they are. So for this particular, I'm showing part of the data set. For this particular event, we had 3 magnitude 2 events that were triggered by the frac itself. Okay, here's another one. You can see, the small amplitudes, but again, think about small alligators.
So it's a horizontal line. So you've got 3 sensors. I'm presuming that the 3 lines refer to the 3 sensors.
Yep.
The first and the third are essentially flat, but the second one has a lot of activity.
Yeah, so that's actually just a noisy sensor. That's the yeah. So sensors are we try our best to protect them, for example, from the wind. We try our best to protect them from running water. But for example, this sensor, the landowner was a small nail salon actually. So we knew it was going to be noisier. It was next to kind of a country road, but there was also like activity, people coming in and out. So we knew it was going to be noisier. But it's the lower frequency stuff that we look for. Okay, so here's an example, by the way, of a truck going by. You can see think of a truck like it approaches you, right? So that it ramps up and then it ramps down. So that made it into the data set. An earthquake, on the other hand, will always be sudden onset and then a tailing off. Okay, and so this brings us to now. We received funding to do a much larger deployment. Because in our kind of ambulance chasing, we proved the fact that we do have suspicious events, but we couldn't really quantify them in terms of their location pretty well. We couldn't figure out some of the more technical details of them to conclusively tie them one way or the other, which is something we want to do in this second phase of the study. Okay, so here are 2 study areas, kind of the greater Binghamton area and the we call it the greater Pennsylvania area. Okay, right, kind of it's the mirror image of this. So we're sitting right here at Copernicus. We are really interested to basically put stations across the border from New York, going all the way into Pennsylvania, and see if we can basically take a look at what we see. And we need your help. And this is my pitch. Okay, if you would like to host a station, we will gladly have one brought to your property. We can't pay anything. It's a publicly funded project, but we are known to bring coffee. We are known to bring good conversations. We'll talk to your ear off about earthquakes. We'll show you everything how it works, and we will acknowledge your participation in any publication that we do. So if you're interested in hosting a station either on the New York side or the Pennsylvania side, we will be very happy to talk to you further. Yeah. Not very close. No, it's you know they're pretty sensitive. Yeah, so we're talking within 20, 30 miles even. Yeah, so yeah.
I got a friend who lives in Scotland. They own 10 acres of land. It's quite hilly.
Mm-hmm.
Actually have an observatory on it.
So this is New York side, right? Yep. So for the New York side, we were very fortunate to host some of our stations right here at Copernicus. But we're always looking for more stations. Yeah, if you want to host them, you have somebody who wants to host them. We are more than happy to. Again, we're a fun time. It's very non-invasive. It's a hole. It's similar to planting a tree. That's about it. We will cover it up for you.
Are the containers you've got, are they critter proof?
We hope so. So critters are our worst enemy, by far. And we have had everything from small kind of gerbil things to bears. Our bigger problem is actually humans, because we have solar panels on these things, and solar panels, man, they attract bullets like you wouldn't believe. People just love shooting those things. But that's a known thing. That's a kind of a trick of a trade. We tried all sorts of things. We put American flags on them. We put other stickers on them. Nothing seems to help. Like, people see a solar panel through their scope, and the bullet goes right through. So we have like there's albums of pictures of these things. We keep them. And unfortunately for this deployment, for the previous one, we actually used, because they were so short, we just used a 12-volt battery. So they were kind of a little bit more discreet, but these ones will have a solar panel on them, which is also a little bit more sensitive. Okay, so yeah, this is my contact info. My collaborator, Tim Desmet, he was not able to join me today. He's teaching. But this is what a station looks like. This is a typical setup. Here's a solar panel, the infamous, best shot. Target, yeah, it's a target. It's yeah. Little container, little hole. This is actually smaller than even we would do here, but that's about it. I really want to thank our graduate students who contributed to this. So Chelsea and Trisha and Yaron are amazing. They've persevered through digging holes and driving out to faraway places to put these in. So you will probably, if you want to host us, you will meet them. They're a fun time. And that's it. I would love to take some questions from you guys. Thank you so much for coming. So yeah. Of course, yeah, and I'll be here. So. Okay,
what we're gonna do is, if you have some questions, I'll do the Phil Donahue thing, and I know I'm dating myself on air, so that the people on the live stream can also hear the questions. So, you have any questions you wanna ask? Right, hold on. Here we go.
So you put the fluid, the wastewater, underground under pressure, but I thought liquids, by definition, are not compressible. So you put more pressure on, it's just going to break through something, is what you're saying.
Right. So the liquids are not compressible, right? But the pore space is. Right, so you're increasing the pressure inside the pore space, because there's the pore space. Once you evacuate the gas, right there, it remains open. So you're repressurizing that system. You're increasing when people think about rock, they think of something solid, right? But so for example, a brick. How much pore space do you think a brick has? Like, how much empty space is inside of a brick? 5-10%. It's more like 30. Yeah, for a brick, it's anywhere between 30 and 40%. Yeah, actually, like even a basalt, something that's completely solid, that's about 5%. The industry considers something that is between about 17 and upwards, 25 and upwards. That's reservoir quality rock. So it means that the ratio of empty space that could be filled with fluid is 25 to 75. So that's the
Under the pressure that. The fluid isn't under pressure.
The presentation.
Yes, exactly. Yeah.
And then equalizes once the volume hits whatever.
Yes. Yep. Mm-hmm. Do you have a question?
She wanted to see what's inside your laptop.
Oh yeah, cartoons always. My daughter did the same thing.
Get another question in the back here. Hold on.
Yeah, my question is, New York State has natural gas wells out west.
Yes.
Is that part of your study as well?
So the New York State has gas wells. It does not have horizontal wells. So that's the big difference. New York State has we have wells in Binghamton that were drilled in the 90s. There's a shell well actually on near one of our retired professors' properties. So New York State is not, we're not foreign to oil and gas. As a matter of fact, in the 1800s, New York State was the world's largest producer of oil. John D. Rockefeller did not make his money in Oklahoma or Texas like many people think he did. He did not. He made all his money in New York State. Yeah. So we have wells in New York, and we're actually, I think there's actually a grand total of 3 producing wells. Or I might be wrong on that. So we have overall, I think we have about 61,000 wells that were drilled here historically, and most of them are out west. Olean, Cattaraugus County. Yep.
So what's all the controversy about the wells being, they pollute the groundwater and everything, but your slide was showing that it's going way below that.
Mm-hmm. So this is what gets complicated, right? Most of the pollution of groundwater with frac fluid occurs not at the level of the reservoir, but through the failing of the concrete or the steel on the way up. That's actually, and that's usually the culprit. It's like, imagine you're drinking through a straw, but the straw has holes in it, right? And you're drinking like not like a Coke, but like a cocktail. You're drinking all the way from the bottom of it, but it's gonna come out kind of where it stops. That's the whole casing issue. And so this is where I usually get into trouble. So fracking is a very loaded term these days, right? You can have people sitting on one side of the room defending it to death, saying it's they will drink out of that well 24/7, let their kids drink out of that water well 24/7, right? And you got people that say that every single frac well is gonna kill everything, right? And both are right under the right circumstances, right? You have a perfectly sealed well with a steel pipe and a layer of concrete protecting it. It's a perfectly done job that will never in 1,000 years leak that fluid out. Or you can have the worst job done, and you can have it pollute an entire township. And both have happened, right? And I always compare fracking to plastic surgery, right? Not something you need, but something you want to improve your quality of life. Cool, you made a decision, but now you have a decision as to where you go to get that done. Do you go to Uncle Bob behind the garage, or do you get it done properly? And the problem is, if you do the first one, you save a lot of money. You could potentially make a lot of money. Or if you do it right, that's a very long and convoluted answer to that question. I know that. But it is a very, very divisive topic. And trying to stay even somewhat kind of center of it is probably the worst position, because now both sides hate me. All right? So that's usually the issue. Usually, but if you have a case where there's a deep fault that runs all the way from the top all the way to the reservoir level, you can have migration of fluids. That has also happened. So disaster is always a sequence of unfortunate events, right? And you can have that happen. Because remember, you saw the map of the wells. It's actually right here. How many wells are in Pennsylvania? Does anybody know? It's close to 1 million by now. Yeah. So imagine all the possibilities. Yeah.
So is the idea that because New York doesn't have them, that's kind of a control, so you can.
Yeah, that's exactly right. That's the laboratory, right? We have the world's only controlled study of this. There's no other place like this. Well, maybe like, not even Canada. Canada's actually they love producing. But it's a very unique regulatory framework where we have that, and again, nobody else does. But again, what we try to do is we try to stay impartial. We try not to sensationalize this either way, right? We're not going to tell you. We're not going to come in here and tell you, drill right now. Everything's safe. No earthquakes ever. Okay, but we're also not going to tell you that if you drill, there's going to be an 8.0, right? It's both kind of our. But again, it's about decisions. It's about your decisions as as communities as to how you want to approach this. And the best thing in my opinion, and that's why we're doing this, is get everybody at least on the same playing field in terms of data access, right? You want to be able to log into a website and see, all right, these are how many wells were drilled. These are how many earthquakes they triggered in an area that is comparable to mine, or that is my area, and then you make decisions based on that.
All right. I was looking also on the live stream, although we don't seem to have any questions there. So if people wanted to maybe stay a little longer, you can.
Of course, yeah.
You talk with Dr. Nikulin. But you talked earlier about basalt, and I've got a piece of basalt right here. But particularly, actually, hold on, I'm going to change to the webcam here so that people on the live stream can see it as well. So give me a second. So this piece of basalt is not your ordinary piece of basalt. This actually came down from the moon on Apollo 17. This is a lunar sample that we have on loan from NASA, and there's a little display case over that I'll be putting this on here. So before you leave, you got to check this out. We're very fortunate to be able to have this on loan, albeit briefly. But also, the clouds actually are sort of coming in and out. So we're able to show you the moon, Jupiter, and Saturn. So the rule here is you cannot leave Kopernik until you look through a telescope. I will track you down. So you're invited to basically go back out straight through the doors, the double doors on the opposite side of the lobby here. And we have a scope out in the yard, but then we can invite you into our permanent domes, and you can take a look at the night sky, at least the moon, Jupiter, and Saturn when they peep out of the clouds. So thank you very much, Dr. Nikulin. Appreciate your time. And sorry, you're showing the little insight.
Yeah. So just a quick little note. Again, we talked a little bit about differentiation. We look down below, and folks look up in the sky. But the InSight probe that landed on Mars has 3 instruments on it. One of them is a seismometer. It's one of the most interesting it's one of the most useful instruments in terms of studying a planet. And we are just as interested to what's happening below Mars surface as to what's happening above and on Mars surface. So it's kind of a big deal for the seismic community to have had our instrument put on the InSight. All right. So with that, thank you so much.
Right. Well, thanks again. Again, every Friday night we offer a public program of some sort. Next week is actually going to be a little different. We have another BU professor, but this professor is Dr. Tomo Nishikawa, who is associate professor out of the film department at Binghamton University, and he is going to be doing a short film festival of I think a half dozen artists doing some short films using sort of astronomical images as sort of their basis and experimentation. So if you're in town, doing something a little different, come on up for our film festival. So again, we invite you to head out to the scopes tonight, and when you do leave, just watch for the deer. And actually, when I drive down Underwood Road, I usually drive right down the middle. It gives me a couple extra milliseconds to respond. But anyway, again, if you haven't looked through our scopes, you really got to do it. It's almost every time a person looks at Saturn for the first time, it's just you get this like, oh, I see it, kind of reaction. So thanks you again for coming up, and we'll look forward to seeing you up again here soon.